last time we discussed how to derive this principal component. If I summarize it briefly, if you have a data, let's say vector RT, then data will look like this. Okay. So if it is monthly data, then this is your time axis, variable 1, 2, 3, 4, 5, right? So number of variable in this case is, let's say, 5. And if you have 5 series, then you can calculate its covariance, right? And using this covariance matrix, you calculate what we call eigenvalue, right? Eigenvalue. So eigenvalue 1 through 5. So same as this one. Okay. Of course, this omega matrix is 5 by 5. And we sort it from the largest to smallest. Okay. And also we learned that each principal component, we can calculate, eigenvalue, we can calculate eigenvector. The first one, second one, and the last one. Okay. So what is the dimension of this? Well, because we have 5 variables, so we have 1, 2, 3, 4, 5. So that's the dimension. Okay? The same. Okay, then what we learned is we use this as a weight to calculate principal component. Let's say first one, 5. Okay? So that's the collection of these here denoted by psi. Okay? This one. But we know that the variance of first principal component is simply this one. And the variance of this principal component is this one. Okay? And one of the property is if you add these 5 numbers, then that is going to be the same as the sum of this variance. Okay? Covariance matrix and main diagonal is the variance of each series, right? And off diagonal, these are covariances, right? So sum of this is same as sum of this. And this is the variance of that, right? So what we can do is we can calculate the ratio, like sum of this all of them in the denominator. And if you look at individual eigenvalue, and that's the portion of total variation explained by this principal component. Right? So if you look at this contribution, then you can cut the number up to, let's say, k equals to some smaller number than 5, like, let's say, 2. Okay, that's the procedure we explained, right? So if eViews return you this information, and if you decide where to cut the number of principal component, okay, then all you do is to calculate first principal component, these numbers multiplied by first 5 numbers, And these numbers multiply by the second ones and third one and so on, right? Then you can calculate this PC1 as a sequence, right? To calculate second principal component, we look at second eigenvector and then multiply this way, right? Then we can get the second principal component, right? And in matrix notation, if you form a matrix using this, in this form, and R is this, right? Then by just, if you have your dimension right, then you can calculate this one right away by matrix operation. Okay, so that's what we did. And also we learned when we do this principal component analysis using, let's say, spot rate series for RT, interest rates are non-stationary, right? So what we did was first we take first difference and then calculate this and do the rest, okay? And if you pick any maturity, let's say 3 year, 1 month, 3 months, 120 months, in this case is expressed in months. If you pick any series, let's say D5 as your choice, then you are more likely to find high correlation between first principal component and that. Because it's the level, right? Level. And if you calculate slope in this way, and to make it stationary, take first difference. And if you calculate correlation between this and the second one, it's going to be very high. So in that way, we conclude second principal component from this analysis using spot rates. Second principal component is in fact slope. The third one here is more likely to be curvature. Okay? So this was the exercise for that. Right? So if you have these 3 series, then usually you are explaining like more than 90% of total variation in spot curve. Then this last issue, the importance of first 3 principal components over time. What we do is we set moving window, let's say 60 months, so 5 years. And suppose we calculated the portion explained by, so we just use first 60 observations to calculate this and calculate that and check this. Okay, so first one explained by this much, that much, and that much. Okay, and because it's a moving window, now take second moving window in this way to make this one 60. Do the exercise again, and you continue. So if you click, in reviews and calculate this number using 60 observations, then you can calculate this one. But that's going to be a very tedious job, right? So because it's kind of repetition, you can let a computer program to do that job for you. So in this particular example, using 60-month data, we calculated we calculate the portion of total variation explained by first one, this much. Additionally, second one, sum up to this much, right? This plus that, right? And the third one explained by this much. The total up to about 95%. So if you keep doing this exercise, you can see this whole thing, right? This whole thing. So as you can see, before some period, first principal component explained relatively much less than other period. And the third component, principal component, explained fairly, good portion of the variation, but later on gets smaller, right? Smaller. So, because the shape of your term structure, if you look at this period, a significant portion is explained by the slope, right? So slope means short maturity versus long maturity interest rate, right? So it's a shape of your term structure. So, as a fund manager, depending upon your view about the future shape, this way or that way, you can form your portfolio by purchasing more of long-term bonds relative to short-term bonds, or the other way around, right? Because the slang used in the industry, the level factor means, whether the whole thing will go up or down, right? But it's very difficult, right? Whether the whole interest rate is going to go up or down. People every month make a guess about that by observing the monetary authority, right? In the United States, FOMC's decision, right? So it's very difficult to forecast. But people. So if it is very difficult to forecast, then you can't make your strategy on that, right? Because it's going to be very risky. But some people have some view about this, so they can conduct sort of tilting strategy, expecting flatter term structure against a steep term structure. You can also think of butterfly strategy by making some guess about the curvature, right? But as you can see, the portion explained by that part is relatively small, right? So mostly your betting is more likely to be on this one. So when you go out and be a part of internship program this winter, some of you may be assigned to asset management company, 우리 asset management company and others, and then there probably they will teach you, how to form that kind of strategy. And of course, to set up that kind of strategy, you have to provide some scientific or analytic result that support that kind of strategy, right? So that's what they expect from you as a econ and finance major. Okay? That also means that they expect you to calculate this using computer program and do it right? Instead of using original interest rate series, you use first difference of that. That's small thing, but makes a lot of difference in terms of output. So doing is very important. Practicing. So we had assignment, second assignment. The one I introduced last time was about using this data to form VAR model and making forecast, right? That's got to be a very simple exercise, of course, until you do it, right? You complete it. But this is the second part of the assignment too, using same data. And this data is already in the portal, so you can download it. And basically, this is text data and a Korean treasury bond spot rate for maturity. I believe it consists of 13 of them. And so the first column is a date index. Okay? And 3-month spot rate start from the second column, third, and so on, right? So you read the data, and it says, can you compute 3 major factors? 3 major factors. Okay. And then the correlation with historical counterpart. So check whether this kind of result we observe from US data, in fact, holds in Korean data. So you can check that, and then providing this one. Okay. Well, other than this part, it's not going to be that difficult, but this portion, it's kind of tedious job. So what I did was to provide you this one, pcano.gsi. In the lecture notes, I used this text file where you have this one. So 18 maturity spot rates and 1 time index that look more like this one. Okay. And Korean spot rates is saved, stored in the same format. Okay, for time index and rest. Okay. So if you have that text file as an input, that's there. Okay. And the dimension is going to be different, right? Dimension of this file and the dimension of this file is going to be different. Right? So all you need to do is to check this text file, replace it here, and replace this number and that number. Okay. So as many times 14. You can check that. And then the maturity, this number, in Gauss, if we say, if we define maturity in this way, you're creating a row vector. And if you transpose it, then it's going to be column vector. So typically, if they don't say anything, when we say vector, we usually assume column vector. Okay? So you need to replace that with this one. Right? And then window is set equal to 60 months. And our data is also in monthly frequency. And as you can see here, the data is all first difference. So, these are kind of Gauss code, probably you may not be familiar with right now, right? But the thing is, if you really need to understand what's going on in the detailed computation here, then you have to take a look at closely and understand line by line what they mean, right? But think of this as a big function, and you specify the dimension of the problem and set some parameters and let available program, existing program, do the job for you. Okay, so this is our strategy here. But the thing is, for instance, if you have a data, Y, and what this thing does is, like, to make original data as a first difference, you are trimming the whole thing. If this is whole data, then you are taking from here to there first, and then here to there. So this one is YT, this one is YT minus 1. And taking the difference, you calculate first difference once and for all. Yeah. So that kind of thing is included inside this program, so don't worry about that. And then result will look more like this one, the same as the one you see from lecture note. But if you replace it with Korean data, the result will be different, right? So you can change things a little, and then you get the result. But before we leave this assignment part, Gauss code is basically text. Okay? So this is basically a text file where things inside this and that are comments. Sometimes we use library, in this case, something called p-graph, to draw a line graph. Okay? And let's see. Well, and then let's skip. Well, this is also comment with at and ended by at. Inside that is treated as comment. So comment. Not executed. But if you're a beginner, GB13 text is right here. Let me show you quickly. Look like this. September 2000, October, and so on and so on, right? And then 13 spot rates. So I believe it has something like 145 observations. Okay? So this is the data. And then this is the program, right? This is the program. Currently use 0 yields, right? As I showed you, 0 yield text. The same format, right? Same format. 300 and something, 83 observations. Okay. To run this one, this is Gauss prompt. I'm using version 6, but I believe they have the later version, but they're basically the same. You know, if you press this one, and this is the start of the Gauss program, and if you want to create any new file, then edit, then enter, and this is your new program, right? So you can type things here. Okay. Gauss is very powerful, but you probably feel helpless because it doesn't say anything. So if you run it, nothing will happen because you didn't instruct anything, right? So in Gauss programming, see, it's complaining. So you know, when you actually start writing, before you actually start writing your program, first thing is you have to think very hard and to figure out whether there is an alternative. If you can do the exercise using eViews quickly, accurately, that's your first choice. That has to be your first choice. It's tested, proven, efficient, you know. If everything fails, if you can't find any alternative, then you have to go to the drawing board and start writing your program. Okay? We often forget. Okay. Go back to this one again. Well, if I start this Gauss, and usually if you want to, you know, open file, right? So open. Let's see, where is that program? Class. This one, and I think it's there, right? So here is a text file. Okay, you can open this one, right? But you know, this is the program, and this is the text file, the input. If they are in the same subdirectory like this one, it's fine. You know, if you run this one, then the program will look for the same subdirectory and try to find this one. Right? The thing is, Gauss is installed someplace else, and it has its own directory. It will look for that directory only. Okay? So computer upstairs, if the program is installed in C drive, and probably it will point some subdirectory you may not be familiar with. So what you do is, before you actually do this one, even before you start this program, first thing is check this one by pressing right button and the property. So if you look at this property, it says this program is installed in C drive in this subdirectory, right? But this is the starting position. my document, and right? So even if you open PC anal GSI from Gauss, you cannot read the data because it points to the subdirectory. Okay. So what I used to do is this. If I want to specify this one as my subdirectory, let's see, PC anal GSI, I open this one and take a look at the property, and this is the location, right? So I highlight this and I copy it, and then go back to this one. Here, I change it. I change it like that. Okay? And then if you start this, and if you open, it will point this subdirectory right away, right? So you call this one the same thing. And this is run button. This is run. This in terms of graph, in terms of data. Okay. So if you go to graduate school, graduate students spend a lot of time coding this, make a lot of mistakes, and professors go out somewhere and present nice graph and do the rest. So it's a team play. So if you do this exercise many times, you know, suddenly you will probably develop some idea about how to write efficient code and so on and so forth. Okay. So hopefully you can do this exercise. And as I said the other day, try your exercise as early as possible because the due is 1 week from today. Make mistake and bring some questions on Thursday. Okay. Okay. The last thing is, well, this is not that heavy, but it's worth mentioning. It is called intervention analysis. Vector order regression or univariate time series analysis, we look at just one or multiple time series, and they are endogenous in a vector order regression, right? In this intervention analysis, we want to introduce other variable which is not endogenous. Okay. So you can see, for instance, this is the data shown by Anders. It says installation of metal detectors in all U.S. airports in January of 1973 to cope with skyjacking. So that period is about here. So before and after the installation of metal detector. We want to see whether in fact installation of metal detector is effective. So in the early paper, Anders examined this type of equation where YT could be number of skyjacking, and of course there's some serial correlation, right? And this is intervention. So intervention variable Z is 0 prior to this quarter, and then 1s. Okay. The simple dummy variable, right? And estimated a problem and found this coefficient significant, negative. So introduction of metal detector lowered skyjacking. Okay. So this one was significant, and these are not. So here's, but you know, in general, these numbers could be all significant, right? Then the interpretation is immediate impact is measured by C0. So introduction of metal detector immediately influenced this one, right? Number of hijackings. How about other parameters? If you actually calculate C0 divided by this, then you know cumulatively it's affecting in the long run this variable. So actually this quantity summation and that is measured by this one. So introduction of this one has immediate impact, and then long run impact is this, but this was 0. So actually you don't calculate this number in this particular example. But you know, introduction of such policy could have short-term effect and long-term effect. And if these are significant, then this is a quantity determining long-run effect. Okay. In more general specification, this was the previous specification, but you could have more legs of Y and also moving average time. Right? Or it could be the variable lagged by D number of period. You know, it depends upon your specification. And also the ZT doesn't have to be like zeros and ones. It could be like pulse. It could be like gradual changing. It could be like prolonged pulse. Okay? Depending upon the context of the problem. Okay? So we say that's the ZT intervention function. And also you can include more lags here, lags of ZT. So if you define C of L in this form, so this times ZT. So first one is like C0 ZT, same as before. The second one plus C1 ZT minus 1, and so on and so forth. Right? So if we happen to estimate this more general model and found C0 is 0, then actually ZT is a leading indicator of this one. So if we have here index of coincident indicators, and if you have a leading indicator, then probably you will find several coefficient 0 and then significant. So in a business cycle, you want to find some leading indicator that changes direction prior to this peak, right? And change its direction prior to this trough, right? So if you have candidate variable here y and zt. Then you can estimate this type of model and check whether these are, some of them are 0. Anders also provides this result, terrorism and tourism, okay, in Italy. So number of tourists and number of events as ZT, right? So, so he estimated several alternative models, competing models, and it appears, which model appears to be most reasonable? Is terrorism a good leading indicator of tourism? Well, it appears to be, because, you know, these are in many specifications 0, right? Only lag 1 and lag 2, right? Numbers in parentheses is t-value. So if you look at AIC and SBC, it appears that this combination appears to be good. Right? So no contemporaneous effect, but lagging, right? And some autoregressive part. So that's simple idea of intervention analysis, and I think that's enough. So we'll this concludes our note 5 about multi-equations time series model. Before we move to vector or error correction model, any question? Comments? Lecture note 6 is available from our portal, and it has title Cointegration and Error Correction Model. And this plot may give you some motivation. First, these are quarterly data, and consumption and GDP. Okay. Vector autoregressive model is actually modeling like this change, and this change. Right? But when we look at longer period, okay, there appears to be some relationship. Okay. Loosely speaking, if you find this straight line between these two, then this is sort of average propensity to consume. Right? Average means long, right? Marginal propensity to consume, that's small change in Y, small change in C, right? So if you are working with, marginal propensity to consume, then probably you are looking at some model like vector regression to do that. But here, if you want to look at average result, or we say this is long-run relationship, or sometimes in other contexts, it may be appropriate to call this one as equilibrium condition, long-run equilibrium condition. Okay? And economics and finance, consumption function is a well-known example. There's a long-run relationship between level X, level Y. Okay? But before we say about this one in a vector autoregression framework, many people are worried about the possibility of spurious regression. Right? When you relate our cost P with number of casualties in Western Sahara region. Maybe, if you run a regression using these two, you might find some significant relationship, but meaning nothing, right? But in other contexts like this one, consumption and your income has long-run relationship. Also, there is a well-known model called Gordon model, or we say present value model, or dividend ratio model. It says there should be some sort of long-run relationship between stock price and a dividend. Okay. So that's the quite commonly observed relationship in economics and finance. And so if you are interested in projecting, let's say, next quarter for this and consumption, then you are actually looking at this change, right? But actually, there is a kind of serial correlations, it appears to be, right, over time. But also there is a tendency that it doesn't deviate that far. Right? So pulling things back and then deviate and then pulling things back. That's the equilibrium is by definition, something could be perturbed, but there's a tendency to go back to where it started. That's the idea of equilibrium, right? So, when you project this one, you don't project it this way, right? Because there is a kind of equilibrium. Right? So we'll try to deal with this type of situation in this chapter. So, a simple, to understand fully what we mean by so-called cointegration, we look at some simulated data, where first let's define x2 as a random walk. So this has coefficient 1. So random walk with rate of drift d of 0. Okay. By this, we just simply assume that u2t is stationary residual. Okay. And also define AR1 process, stationary, like this one. And then define new variable x1t, which is sort of related to this one and then that one. So if you look at this one, x2t is by definition I1 process, non-stationary, right? If you add non-stationary variable to stationary one, then of course this is going to be non-stationary, right? Because high order dominates, right? So because this is I1, so this is I1 as well. Okay. But the thing is, these two in level is related by non-zero coefficient 1, right? So suppose that data is generated in this way, x1t and 2t, and we want to see some simulated series. Okay. Let's assume, well, this one was assumed to be 0.9, so satisfying stationary condition, and some non-zero value for these two parameters. And also, as you can see here, x1t and then subtracting x2t from that is this side, right? You can rewrite this one as a vector operation like this. And we call it, linear algebra textbook, this is linear combination, right? Linear combination, which is sum of these two, right? So originally they are I1s. Their linear combination is stationary. Okay. If that condition is satisfied, or we say making this kind of property possible, and if there is a non-zero coefficient, in this case 1, in this case this one. So we call this coefficient as a cointegrating factor, and this as cointegrating equation. Okay. Cointegrating means, see, y on x, y is regressed on x, and this is simple regression, right? Linear relationship. So that is equivalent to finding that. Right? So deviation from this red line is, of course, if in fact it is similar to x1t and x2t, that's going to be this one, right? Which is stationary. And stationarity means, because this is mean level, and it will fluctuate around that line. Okay. And well, here what it says is, suppose x1 and x2 are I1. Then you can go either to VR modeling or the one we call it VCM. Okay? Are they the same, different? Of course, different, right? The name is different, so it's going to be different. But the thing is, well, these variables will change over time, right? So thinking of these two variables in terms of first difference is natural, right? So if you take first difference, then actually you are aiming at this part, right? But where can we include this information? So that's the idea of this. Okay? So we'll introduce this one shortly. But before we do that, if there is a cointegrating relationship like this one exists among variables, and if you ignore this part and simply try to approximate the process as a, VRP, with p being relatively large number, then actually you cannot correctly approximate this one. So, complicated process could be approximated by introducing higher lag p, right? But still not enough to show some of the desired properties shown by this model. I uploaded this information this one on our site. So this one, Y2. Here, Y1, Y2. First, yes means rate of drift. delta 0 and gamma 0 are non-zero. Okay? This group. This one, same thing. Right? So there, when you read lecture note 6, and if you want to replicate the result, then this is your data. Okay. So you can try this one and build some sense out of this type of analysis. Okay, so this one assumes delta 0, which is rate of drift in the series 2, x2t, is assumed to be 0.5. And gamma 0 is the intercept term in a long-run relationship or cointegrating relationship. That is assumed to be 4.5. So go this way. But interestingly, these two series, assuming this as a parameter, does appear to be going, closely over time, right? Because that's what we design, right? But can you tell which one is leading that direction? Which one? Blue, red. Press your button. Which one? Which one? See? You can think of this as, let's say blue one is leading, and then red one is trying to keep up with, or vice versa, right? Which one? Which one? This guy or that guy? It's meant to be a simple question. Don't need a genius here. x2t. If your answer is x2t, that's the correct answer. Why? It is a random walk. Random walk. You never know where to, right? It's a random walk. And then it is determined by 1 times that value added by constant and some noise determine x1, right? So lead and follow. So we say this one is driver. And you can think of, term structure of interest rate. We've seen these spot rate curves, right? Which one is driver? You might be able to do some analysis and find, let's say, 10-year spot rate is driver. And then others follow. Term structure, it never goes this way, right? It's steep or flat, but it never goes to like this or like that, right? Tends to move together, right? Sometimes wider, narrower, right? So there must be something leading this whole thing, right? And sometimes there are others following, maintaining some relationship. Actually, if you build a model where you have KTB spot rate as one series and a spot rate derived from corporate bonds, which is risky bond, right? Treasury bond is riskless bond, and corporate bond issued by firm, company, that's risky bond, right? And the difference between these two rates at a particular point in time is spread, right? Or we call it credit spread. Spread gets wider or narrower, right? Depending upon the riskiness of business condition, right? but it never goes to like this or like this, right? So there might be some relationship, and one of the study shows that actually Korea Treasury leads, so playing the role as X2T, and corporate bonds follow. So if that is the case, then try to predict corporate bond rate. You better include Treasury bond rate, because there is a kind of tight relationship over time. Right? Okay. So we'll see that later. If you let rate of drift of random walk process as 0, so it's driftless random walk, then this one, no, x2, t3, no means this is set to 0. So it's going nowhere, but this time in this particular simulation, it goes this way, purely random, right? So you can see that because of this non-zero rate of drift, it's aiming more or less this way, right? But because it is set to 0, now it's wandering either here or there, but not showing strong trend, right? But anyway, still these two series shows a tight relationship over time, governed by this long-term relationship. Okay. Then, if you are given, let's say, these two sequences data without knowing the data generating process, then you have to be able to test whether there is, in fact, this relationship. Okay. We know how to conduct unit root test, right? Augmented Dickey flow test, right? See? If you have, let's say, two variables, x1t and 2t, and testing for cointegration requires, let's say, first run a regression of either this one on that or this one on that. Simple regression, okay, simple OLS. Then you can compute residual, right? Residual. By running a regression, simple regression, what we mean is we find the relationship between these two here, up to here. So you could find some coefficient, let's say 1, or 1.2, or 0.9, some number, right? In terms of level, original level. And then fitted residual. So if they are in fact co-integrated, then this has to be stationary, right? So from first regression, obtain fitted residual from level regression using OLS, and then test whether the residual has unit root. Sorry that I'm moving back and forth too often, but suppose they are not co-integrated. If they are not co-integrated, then this is going to be 0, right? Not 1. This is going to be 0, so no relationship, right? But if you have I1 and I1 time series, then this has to be, this can't be this one, right? Because I1 has to be I1, right? So if you assume this one, that doesn't mean that this one has to be I0. This equality will not hold, right? So what I'm saying is, suppose you test it and know x1t and 2t are I1, non-stationary variable. Okay. Then run a regression, and if they are related, then this one is I0. If not, because you said this is I1, you will find this I1 same as this one. This is going to be I1, right? So very simple to conduct the test for the presence of unit root. So if you, let's say, if you find unit root, that means things are not correlated, are co-integrated. Okay. If you reject the presence of unit root, which is equivalent to saying finding stationary process for this one, then you are finding evidence for co-integrating relationship. Okay. Just remember one thing. If U1t is found to be stationary, then they are co-integrated. If you find unit root from here, then no co-integration. Okay, simple as that. Of course, you can calculate this U hat t from running a reverse regression, right? Changing the role of dependent and independent variable, switched like this. But usually the result will be very similar. But the problem is, if you have three variables, three I1s, and try to fit the model, then let's say running a regression of x1t on constant, x2t, x3t, and you can get residual, right? You can also apply unit root test and determine whether these are in fact co-integrated. But the problem is, if you have, let's say, more than two series, so in this case 3 variables, maximum number of co-integrating relationship is 2, known to be 2. So number of variable minus 1. Number of variable minus 1. So how to find second, if any, second co-integrating relationship? Can't do that, right? There is only one regression, right? It's very similar to the situation where we find different weights to find principal component. Unless we do it, apply some trick, you can't find different weights, right, to construct psi 1, psi 2, psi 3, right? Likewise, we need some trick to find co-integrating relationship if there are more than 2 variables. Okay? So that procedure is known as Johansson's co-integration test. So basically, idea, well, this is a very technical paper, but these days the logic is well understood, and so you don't have to worry about every detail of this. All you need is how to properly apply this method to real data. Okay? This is a vector version of unit root test. Right? This one. So if it is vector, and if it is VAR1, and subtracting xt minus 1 on both sides, and this is what you get. Right? So if you define this as lambda, capital lambda, then we need to take a look at the property of this one. Suppose suppose this is simply univariate time series. X is univariate. And what is the implication of finding lambda 0? If lambda is 0, that means xt equals to xt minus 1 plus this, right? So that means I1 process, right? Unit root process. Now this is vector. What is the equivalent term for saying this is 0? We look at rank. Rank of matrix. If rank of matrix turns out to be 0, then it says all component series are integrated process of order 1. So that means they are just I1 series stacked, but they are not, there's no long-term relationship among them. Okay? So this is the case. If rank is n, so there are n elements in X, so this is n by n, this is n by 1, n by 1, n by 1, n by n. Okay? Then if rank is 1, n, that means that is equivalent to a situation where, in a univariate case, this is a non-zero. Non-zero. And in fact, all of them is non-zero. So that means xt itself, all the elements in xt, they are just stationary time series. Stationary. If all 0, everything I1. If it has full rank, n, then all the series are stationary. And in between. Okay. So if it turns out to be the case that the rank of this matrix lambda is some number less than n but greater than 0, that in that case, actually the cointegration test means, well, there are linear combination of x's that result in stationary series. N number of linear combination is going to be stationary. That means there are n number of cointegrating equations. Are you with me? So without seeing any technical detail about the test, the situation is just like that. Okay? So we'll get to more detail. Here in notation, x's are individually I1 stacked together. Suppose in level, original level term, suppose they are VARP process. Or in short notation in this way, okay? Then, you know, if you define this is in Greek zeta. If you define zeta using those matrix of parameters in this way, and so that's the definition of zeta I, and this is zeta, which is simply this one. So all the coefficients summed and subtracting identity matrix. Okay. So if you define it this way, then it's known that you can rewrite this expression as this one. So, see that? This was VRP. Now you're looking at the change in the variable. So this is all I zeros, right? And it has a lag, serial correlation, because it has serial correlations, right? But because of first differencing, lag stops just before, prior to this one here. T minus P plus 1, okay? And then same alpha. And this is a level. This is a level. And zeta is defined, which is the sum of this minus identity matrix, right? So from here to there is simply rewriting the same thing. But do you see the similarity here between this representation and this representation? If you ignore this part, that corresponds to this, this, and that, right? And as I said here, the testing, whether there is a cointegration relationship, we look at the rank of this one, right? So in this case, we look at this one, rank of this one. Okay? And in fact, the theory goes from here. Well, if there are number of cointegrating relationships among n component series, then this zeta can be decomposed in two parts. So this is the theory part, where if the rank of this turns out to be R, which is less than n, the dimension of these two matrices is going to be R, n times R. N times R. So let's go back to this part first. Okay, suppose this is the case. This is the case. Well, if you multiply this A transpose to original data, and let's call it ZT. Okay? Then previous derivation, this one. So first plug this in here. Okay? And then define ZT this way. Then this is same as this one. Right? And we call this one as vector error correction model. So we'll get to more detail from here next time. But here, see, first this term, 2, this is the way it's written, right? We say A and B are n by R. N by R, right? So what it says is, suppose you have xt, x1t, x2t. Let's make it 3. x3t. And so n is 3, Suppose R is 2. A is transposed, right? So it's going to be now 2 by 3. So 2 by 3. Right? So do you see this? Linear combination. First linear combination. So this ZT let's do it later. So if you find non-zero of this, and that means you have linear combination, and if they are in fact cointegrated, and number of cointegrating relationship is, let's say R equals to 2, well, that means this is what we call equilibrium error. Okay? Similar to this, right? Equilibrium error. Now we have more variable and we have second line. So we have 2 equilibrium errors from each cointegrating relationship. So what it says is, well, X is going to evolve in short term following by this autoregressive process. Right? But if you look at equilibrium error, previous period, let's say equilibrium error was 0, 0. So you are on exactly on the average line. Okay? Then 0 times B don't affect anything, right? Well, suppose your equilibrium error is negative or positive. Then multiply by this coefficient, that will change this one. So equilibrium error is corrected next period by changing this one. So why X change over time? Because of short-run dynamics and the feature here that tries to correct equilibrium error. So that's the basic structure of vector error correction model. So the rest is basically how to then find R, magic number R. So that's going to be first target next time. And the second, unfortunately, depending upon the way you think of data generating process of this guy, X, there are several different variations of test procedure, which leads you, often very different result. So you have to choose which one is more close to the truth. So this is first target, and the second one is the way we correctly interpret test result and find more reasonable model than doing the forecast. Okay, so that's our what's ahead. Okay, that's all I have to say for the day. And any questions, comments?